So nitration of these compounds give product with proton NMR spectra that are shown. So this is the part that I gave you. I gave you this aromatic compound plus this gives you these results. This aromatic compound plus this gives you these results. This aromatic compound plus this gives you these results. So what I actually did was I took the products of these and then I predicted an NMR spectrum with some software that I have in my laboratory. So if it's hard to see this, you can zoom in on it in Adobe Acrobat. So everything will be posted as PDF. So if you zoom in on your computer as Adobe Acrobat, this is not a picture, this is vector graphics, so you can zoom in as close as you want and you should be able to see any level of detail that you want. And I think that, so with this, hopefully this is relatively straightforward. So you can think of this molecule can be thought of as being equivalent to 2 times toluene. Right. Is that for the first nitration, you can get donation this direction or this direction, right? And you can imagine that instead of getting donation from the CH3 group of toluene, you just imagine that it looks like this. So this becomes because of each substituent, this becomes an ortho para-director on both of these. So again, if you think about, then the question becomes, is it going to go ortho or is it going to go para? Well, there's a couple things that you can look at to give yourself a hint. So there's only 2 sets of resonances. So you know that there has to be a very high degree of symmetry in this molecule, right? So you can rationalize this either by understanding the chemistry or by just rationalizing the symmetry of the signals that you would get. So the chemistry, you would rationalize it by saying, all right, so this is an ortho-para director at both places, so either ortho or para, either ortho or para. And then hopefully you can see that there's a much higher steric demand at these positions, at the ortho positions. And so then you would probably say, okay, it's probably a para director. And then the question would be, well, how do you know that 2 of these will add? Well, you know that 2 of these will add because of looking at the hydrogen spectrum. So if you look at this molecule and you see that, all right, there's a C2, there's a mirror plane in this, not a C2 plane. There's a plane of symmetry in this molecule. So that means that this hydrogen, this hydrogen, this hydrogen, and that hydrogen are all equivalent. They are identical. And this hydrogen, this hydrogen, this hydrogen, and this hydrogen are equal also. Okay. So then you come up with this structure and you can rationalize the NMR spectrum. Alright. So the same thing here. This is actually sort of an interesting example. So what happens here that's sort of interesting is both of these are ortho-para directors. So they'll either be directing here. So if you look at this chlorine, it'll be either an ortho-para director. This one will be a ortho or para director. So you can direct to pretty much any site. And so then the question becomes, well, can you rationalize this with the number of signals and then the coupling of the signals? So it turns out that if you put your nitro group here, So you can chemically rationalize these to go to any of these positions, but then you have to look at chemical shifts and then splitting patterns. So you know that because you have two signals that are very high, that means that you have two hydrogens that are next to the nitro groups. Okay. And so one of these, this will be the one at 8.3. This will be the one at 8.1. And then by default, this one will be the one at 7.6. Alright. But you can also rationalize this from the splitting patterns. But I think the most important way to rationalize this by seeing that you have two sets of resonances that are very far downfield. So that means you have two hydrogens that are vicinal to the nitro group. And then this is a relatively straightforward example, is that fluorine is going to be an ortho paradirector. Then the product of this is only two sets of resonances. So this and this will be identical. This and this will be identical.